All right, welcome to one of days like 6 through 8. We're going to do a couple of examples here, just highlighting the tools for this particular GeoGebra uh, program and how you can use it to do some calculations and stuff like that. So we're going to work on this first example here, given the points to P1 is -4, 2, P2 is 8, 1, and P3 is -3, -6. We're going to evaluate these different vectors, or we're going to construct these different vectors and then do some operations on them. And then we'll move into three-dimensional space and then look at how to generate surfaces and stuff like that. All right, so let's jump over to GeoGebra and get started having some fun. So here is this GeoGebra Classic 6. And to get to the three-dimensional, I go over here to zoom and or to the little pancake thing here. And I click on 3 dimensions because normally the graphics version is open. And then I do want the algebra window open so I can input functions. Okay, all right, so let's go ahead and define our first point here. So I'm going to call it P1, and I'm going to set that equal to the order pair -4, 2. And now notice I'm not putting in the third component as 0, but if I did, since it is in 3 dimensions, you can see that it did pop up there on the XY plane, which is the gray plane here in the on the right. Okay, so I'm going to plug that point in, and I have P2 is equal to 8, 1, and 0. So you can see that that one kind of showed up a little bit off the screen there. To adjust this, I can move my mouse over, and then if I hold the shift key down, I can kind of bring those into the fold, so to speak. And so now it's on the plane. And then I can do the same thing here to kind of keep those, maybe leave a little bit scaled, okay? And I can move the plane. So this is actually the XY plane there, you can see. So those are the 2 points, and the Z axis is kind of coming out of the board. All right, and then I think I have a third point, P3 is the order pair -3, -6, and 0. Again, that one popped off the charts down here, so I'm going to hold the shift key down and bring in the Y values a little bit. Okay, so those are my things. So now I want to form a vector between each of these. So V1 is going to be the vector, and now I can have the points defined. So it's going to be the vector from P1 to P2. So I go P1 to P2. And so it's pointing. So the tail starts at the first point and it points to the second point. So that's the exact value of what I wanted there. So it's V1. V2 is going to be a vector, and it's going to go from, what do we say, P2 to P3. So P2 to P3, there's that vector. And then vector 3, V3, is going to be a vector from is going to be a vector from P1 to P3. Okay, all right, so there are three vectors. All right, and now let's do some operations. So in the examples for 1 at A6, I did V1 plus V2, I believe, yeah. And so there is the example of V1 plus V2, and you'll notice here that the sum of the vectors puts that vector here originating from the origin. And a unique thing about vectors is that they are in a sense coordinate free. So having the vector originating from the origin is okay. Normally we think of the vector as originating from the location of the two sums, and that forms a parallelogram. But this is it's the direction and magnitude of the vector that matters, not the relative position, since vectors can float around relative to one another. Okay. All right. So there's V1 plus V2. Let's look at 3 times V1 minus, I should point out that when I do 3 times V1, notice that you get a vector here whose length is literally 3 times the length of V1, and it's in the same direction as V1. So it's 3 times as long. Everything else about it is exactly the same. And so go back to changing that real quick. So let's delete this and delete and delete. Okay, so 3 times V1. And then what do we want to do? We wanted to subtract 2 times V2 from it. Okay. All right, so there's the resulting vector, and you can see it's there. And then we wanted to take the norm of v1 plus v2. So you can do this a couple different ways. For me, I like to do it kind of all in one place. So one of the ways that we talk about the norm is it's the result of the dot product, which we cover in the next section. However, we'll go ahead and talk about that now. So we have the dot product of v1 plus v2, and we're going to dot that with v1 plus v2. So that's dotting it with itself. If you do that, you get so this is the dot product squared, and so the norm of this would be the square root of a, which would be that. Okay, or you can put it all in one thing where you do the square root of the dot product of v1 plus v2 with v1 plus v2. So it's dotting it with itself. Then again, you get the same result out. So this is the magnitude. This is the length of that vector, which is the last thing it wanted to compute for that example. Okay, so that's all of that first example in V1, or in example one for one at A6. The fourth example is going to be exactly the same thing, just in a different geometric configuration. I guess the last thing would be possibly to look at the midpoint of the segment. So we can do midpoint. So you can do a midpoint of a vector as well. So if you do, let's say P1, this is going to be, notice the difference in capitals versus it's going to be -2, -3, -4. And so this one is off the XY plane because it's now in 3 dimensions, and then P2 is equal to 2, -8, and 7. Okay, those are our two. And then we make a vector P1 to P2. Okay. Let's do P2. Not sure what that is. Okay, well, I'm not sure what that error is, but anyway, theoretically speaking, okay. I don't know if it has some defined other value because maybe it's not Q sensitive for one. D2, W plus D. Or maybe it's just treating it, it's already treating it as a vector, so it doesn't need it, I guess. Maybe that's what's going on. Huh, that's interesting. So I want a vector between them. All right, let's pause here since I hear we clean the slate, and we're going to jump into one at A7 now. So this is example one from one at A7. So we're going to say V1 is equal to the vector from O, the origin, to the point 1, -3, 2. Okay, all right, so there's that vector. And then V2 is going to be the vector from O, the origin, to the point -2 to -5. Okay, all right, so there's those two vectors. To find, this is example one from one at A7. So to find the dot product, you just can say dot V1 V2, and that'll give you -18. Suppose we wanted to know the angle between these two vectors, then we can use the cosine inverse or arc cosine. And here we're going to do A, which is the dot product of the two, divided by A, the square root of V1 of dot V1 V1 times the square root. This is just the magnitude of V1 and the magnitude of V2, V2 dot V2. Okay. And so that gives us then that the angle between the two vectors is 147 degrees. And does that geometrically make sense? So here is V1, here is V2. And does it make sense that that vector angle between them is 147 degrees? And it definitely does look like that is the a reasonable approximation for the angle between those two vectors. Um, all right, what else can we do? To check if two vectors are perpendicular, the dot product is what we need to calculate between the two of them. So in example 3, let's create the vector u, which is going to be equal to the vector o to the point 1 comma 2 comma 0, and v, we're going to equal the vector from origin to the point -10, 5, 0. And so we look at those two vectors, which are these two vectors in the xy plane here, they look like they're not quite perpendicular. However, let's verify that. So if the dot product between u and v is 0, then they are, and if it's not, then they are not. So it does turn out that those are 0, and so that is actually a right angle. So it gives you a good indication that visually it doesn't look like they are, in fact, perpendicular, but um, mathematically they are. And so it is the case then that those two vectors are, and so it'd be these two. Those are in fact perpendicular vectors. So that's really great to see. What else can we do? Um, let's see. I guess I should pause. So I guess we can show the cross product. Yeah, let's do that. Okay, so the cross product, uh, oops, cross the UV. So this is a vector that's perpendicular to those two vectors, and so that is just simply how you could create those two. So if we cross U1 and V, or V1 and V2, cross V1 and V2, okay, and let me shut off these vectors, okay, then you see here there is the angle for that. Sometimes that plane is distracting. Let's see. Okay, so here's V1, V2, and then this is the vector that's perpendicular to them. Let's see, 11, 1, -4. Yeah, so this vector here is perpendicular to those two vectors. So we made the plane, or we could write the plane with that, what this is the normal, and V1 and V2 would be the two vectors that would span that plane. So that's another thing that we can do. Let's see, let's pause here and look at what the other one days have to offer. All right, so we're going to show a couple other things just to wrap up this little video. Specifically, this is from, we showed you a couple different things from different one days. So this is finding one a day 9. And so in this one a day, we're really going to focus here on example 2. So we'll take these 3 points. Actually, 3 points are kind of boring. We're going to kind of play around with this idea from example 2 at least, and then we're going to find the area, the volume, and then the equation of the plane from these, which means we'll also find the normal. So we'll use the cross product and the dot product in these calculations. But to kind of give you an idea of how to use these, and then also you know what to do. All right. So let's play around with this. So I'm going to jump back over to GeoGebra, and we'll play with these ideas. So let's go ahead and clear the screen here. Okay. So let's just create some points here. So how about we make P1 equal to 1, 2, and 3. There's our first point. P2 is going to be equal to -2, 1, and -3. And let's see, P3 is going to equal something fun. How about 0? No, that's a 0, comma -1. Sure, -1, comma um, 2. No, 3, 2. There we go. Something like that. Okay. So think our vectors. So we have vectors. So we're going to find our vectors here. So we're going to do 0, or oh, the origin to P1. Oh no, we're gonna create the vectors from these points. That's right. Okay, so we're gonna do vector, so P1 to P2. We're gonna do vector P1 to P3. Okay. All right, so those are our two vectors. So we're gonna find there they are. You can kind of see them spinning around. Ooh, fancy. Okay. All right, so you can see that P1 and P1, P3, and P1, P2, those two vectors, they form a plane. And so let's find the vector normal to these two vectors to form that plane. We're going to cross U cross V. Okay. And so there's the normal vector. And so you can kind of see that makes sense there a little bit, right? So if you look at it from maybe this angle, you can see that this vector is perpendicular to the plane that would be kind of coming out of the screen right now. Okay, so you can kind of see. So there's the normal vector, and again, it's the relative position and magnitude or direction that matters here. Okay, and in fact, we could actually create a unit normal if we chose to, um, a unit vector, the which would be W divided by the square root of dot being W with itself. And so we could choose to make this the normal vector. Let's see how cute and tiny it is. That's a unit vector. Its length is 1, but it has the same direction as the original B, and that would be just a directional case. So should we choose to use that? Okay, we'll use W, but that is the case. Okay, so then the equation of the plane that we want is we want the normal vector, and we're going to dot that with a vector um, that includes one of the 2 points. And so I usually use the first point, but P3 might be a really good choice too, since its x component is 0. But I like, just for simplicity, I use the first point usually. And so we're going to have a vector that would be the dot product of W with the vector through the point 0 and P1. Would be the point X, Y, and Z minus P1. I don't know if it'll actually calculate that. Yeah, it doesn't like that because it's a function. Okay. Oh my God, that's so annoying. So that's what we would calculate. What it basically means is that you get a plane with you get the negative 17, that's the x component, and then it would be x minus the x component of P1, so x of P1, okay, plus the y component, 3 times y minus the y component of P1, and then plus the z component of W, which is 8 times the z minus the z component of P1. Okay. And so there's a plane that this defines, and that would also, we should say that equals 0. For this, oh, let me duplicate. Oh, and put this there. And so this whole thing would equal 0. And there's the plane. So that's actually what we need to put. So I don't want to. Otherwise, the problem is GeoGebra thinks it's a surface, and so that's why it wasn't showing up previously. So the whole thing is equal to 0. And so there you see the plane is here, and the normal vector is coming directly out of it. And if I shut off W, you would see that the unit vector happens to be kind of hard to see it right there because it's kind of short, but it does go straight through at the direction along W, which is through that point there through the plane. Okay, so that defines then the plane through that point with that normal vector. And then we can also determine the area of the parallelogram that is formed by the two vectors P1, P2, and P1, P3. So that would be the magnitude of the cross product. So if we do the cross product, that forms a vector. And I think we did that already. That was how we got W. So if we take the square root of dot W with itself, this gives us the area. So the area is 19, roughly. And if we thought of a volume with this, let's say we had another vector. Let's just say that this spans, and then we have a vector that goes up to some height. Let's say it's a vector from the origin to the point P3. Let's see. Well, let's say we have the vector. Vector. What can I say? Vector. Think of the. Let's think of me. Let's say it has a height of 1 Okay. All right. So then we could figure out the volume of the parallelepiped that is formed by this plane and the vector C by taking the dot product. So we can dot C and W, and that would give us then the value of the volume. And then if we take the absolute value of the dot product, that gives us then the volume of that parallelepiped. So we can do that real quick by calculating absolute value dot C with W, and that gives us then the volume of this parallelepiped from the plane to the vector. Let's see. Let's change the color. See. Let's make it red. Just make it stand out. Okay. All right. So there would be the volume that we're looking for. So it'd be the plane up to this height here along that. So it wouldn't be a very big one, but just imagine like we filled that space up to the height of the volume from. Let's see if I can zoom in a little bit here. So there's maybe a better view. So what we're talking about here is the volume from the plane kind of up to this, like this perpendicular height between these two. And it makes sense that the volume would be negative in sign because the volume is going backwards to the plane. In other words, it's opposite the normal. However, in magnitude, the volume would be +6. Okay. All right. So we figured out how to do area. That was the magnitude of the cross product for a parallelogram formed by two vectors. We talked about how to find the normal. That's the cross product of the two vectors that form the plane. We talked about how to find the volume. That's the dot product, or what's called the triple product of the vector, the normal. Sorry, not the normal. The vector that make up the plane and the product of the dot product. So I guess it is the cross product or the normal vector times dotted with the vector of heights. And then we talked about how to find the plane, which is the normal vector dotted with x minus a point in the plane. Typically the one that you use to form one of the coordinate vectors for the plane. Okay. All right. And that's how you compute them with GeoGebra. So I hope that was helpful, and hopefully I'll see you in the next video.